Today's video is going to be an act in three parts. First, we are going to test a closed loop system to actively control the humidity within a box. So here I have a humidity sensor for the room. Inside the box I have a humidity sensor for the box. I just placed it inside, and we can see that the room sensor and the box have been at about the same level. Okay. The box just shoot up a little bit, but it's not really important. The delta is not really important because what we expect is a significant difference between what we have in the box and what we have in the room. Okay. So what is this? Here we have a Peltier module and a box with the cold side, a pipe that goes at the bottom of an hermetically sealed box and come out from the top of that hermetically sealed box into a pump. So this pump, the airflow goes this way. So the air goes here, cannot stand this, comes into the pump, shoots here, right? And what we expect is, since the box is airtight, this creates a vacuum in this tube here and pulls the air from this cold side of the Peltier, right? Now we shoot the air onto the radiator with a small radiator. The Peltier module here is very similar to this one, except it doesn't have this fan. The air comes here and we expect the suction, the vacuum created inside the box, to pull some of that air back into the box. Okay. So looking at the humidity inside the box, right now we are around 70% of humidity, and for your information, the room temperature is about 30 degrees. Okay, this moves a bit here. It's a margin of error of this type of sensors, and the fact that I'm not in an air conditioning room and there is fans, so I expect this to be within the margin of error. So let's hit this off. 12 volts, 6 amp max, and let's go. So the cooling fan for the hot side of the Peltier is on. That's good. I can hear this little this little pump, which does about 2.4 liters per minute, is on. And it would be nice if he makes a little less noise. And what we expect here is, what we would like to see is for the box sensor humidity to go down. Right? So let's wait a little bit and see how fast that goes. Of course, those things, they are pulling every few seconds, but here, all right. So we have one data point that came. The purple one is a box sensor, and the humidity went down from, let me remove the room temperature now, perhaps, and down from about 70 to 63. All right, first point, data point 68, second data point 63, and let's wait a few minutes. I expect this to go down to about 30%, perhaps below. Now, while we wait for this to happen, we can look at the temperature, and we're going to notice one thing, is actually that the temperature doesn't change, right? So it's expected this system is not, from a thermic point of view, very efficient, meaning that this box is not insulated. The different pipes are not insulated. This one is not insulated. It does feel cold to the touch. So by the time the air gets into the cold side and comes back here, well, it's going to warm up again. It's not going to stay cool. So we don't expect the temperature inside the box to go down. But what we want to see here is the humidity inside the box to go down. And so far it's quite effective and very quick, right? 52, 48. We'll probably speed that up in post-processing, I guess. 44. So it does appear that so far, right, at every pool, we actually removing about 4% of humidity. This is something I really like because it's really quick, right? It's really quick to go down, and so far it looks very efficient. Now, full disclosure, this is not really efficient mechanism. It has a hole at the bottom, and the hole at the bottom is actually for the water to get out. I expect that maybe some of there's definitely some gaps here and there, and the box itself was not very well built. That's my first design, so it's kind of breaking. You can see a lot of gaps. This is not a very efficient mechanism. This here is actually tight enough, it should be okay. The box itself is airtight, so should be okay. In this design myself should be okay. But this is not very efficient. So far we are still within 4 to 3% at every pulling. It will slow down. We can kind of already see that. It will slow down, but I am curious to see where does it stop. 6 minutes later, we had 31%. So this is quite quick. We are still going down. We're still going down. Let's see in 5 minutes. And we reached 25%. See, the rate of progress has gone down, but we haven't stabilized. We are, however, at 25%. I really would like for the final system to reach below 20% at this range of temperature. It's very important to consider the temperature. 20% at 30 degrees. But here we're still going down 24%, so the rate of change has slowed. We are at 1.3% per pulling, which is about every minute, is it? One minute and 40 seconds. Minute plus. Right, so let's see in 10 minutes where we are, about 10 minutes later. It does look like the system has stabilized around 21, 22% of humidity. Okay, so this first act is actually quite encouraging. So we could imagine this sitting outside an AMS, two pipes going in and out of the AMS, and a system that PMW system, some form of modulation to maintain the humidity level inside the AMS at a certain level. Now, assuming the AMS is as airtight as this, which is a huge assumption, and we'll see that in Act 2. I expect this to be actually cheaper to run than eating up the full AMS, as other people have been trying to do. Few things to notice. This is about 50 watts of energy. It is a lot, but if I turn it off right now, right, I do not expect that level of humidity to shoot up very quickly. So the assumption here is that I should be able, if I reach a level low enough and a certain tolerance, I should be able to switch this on and off to maintain a level of humidity in this box. I will actually let it run for 10 or 20 minutes so that we can see here, but this is really airtight. I do not expect the AMS to be that airtight, as airtight. A couple of things to notice here. The air that is leaving the box due to the vacuum in the box actually, you see, is humid. It's cold, so the humidity around me, the air around me, is actually creating condensation into this on the outside of this pipe. This was the case on the side of the box here. This was the case on the other side of the box, where we do have humidity condensation. So this is a point where we could improve the system, so at least around the box, so that it's colder in the box and more of the air arriving here condensate into this box. But you see, we stop the system now, and it seems that we are stable now. This, of course, is going to go up. The humidity in this box is going to go up over time, but I do expect that it's going to take perhaps an hour to go to 30%. So if we modulate this well enough, we could maintain a certain level of humidity into this box. Now we are ready to move to Act 2. Act 2 is we take an AMS and we see if we can reproduce this with an AMS. Let's try.